Now, last week we were looking at order of elements of a group, and we looked at the order of an element in an additive group. For instance, the order of an element R in the group Zn. We also looked at the order of an element R in the group, in the multiplicative group. Now, and after that, we also define two groups multiply together. These are direct product group. And we saw how the elements of this group look like. The elements of this group are pair AB, where A is the element in this first group, and B is an element in the second group. Now, so we want to look at what is the order of this element in this group. That is what we'll be looking at this time. The order of an element in a direct product group. Now, it's just the same concept as the one we looked at last week of the order of elements in the single groups like the ones we have here. For an additive group, what we said, the order of A is the number of times you would add A. The number of times you would add A to get the identity 0. And so we said the order of A is G if G multiplied by A gives us the identity. In other words, the order of A is G if at all adding A G times gives you 0. That's what we meant by that. If at all adding A G times gives you 0, and then G becomes the order of A. So I'm just doing this to remind ourselves what we did. So for instance, supposing I have this group, Z3, this is an additive group. And then somebody asks me, what is the order of 2? What's the order of 2? So the answer is, how many times am I going to add 2 to get 0? That is the answer. So 2 once will just be 2, and then 2 twice will be 1, and then 2 3 times. 2 3 times gives me 0. 2 plus 2 plus 2 give me 0, because 2 plus 2 gave me 1, mod 3. Mod 3. Because of course it will be 4, but 4 mod 3 is 1. And then 2 plus 2 plus 2 is 6. Mod 3, that gives me 0. That means the order of 2 in this group, therefore, is 3. In other words, I'll add 2 3 times to get the identity. So that is how we look at the order of an element in an additive group. Just reminding ourselves what we did. Then in the multiplicative group, like this one, what was the order of A? The order of A was the number of times I would multiply A to get the identity 1. That is the order of A. The number of times I would multiply A to itself. The number of times I would multiply A to get the identity. So for instance, let me take a group like Z3, multiplicative group. So then I'm asking myself, what's the order of 2? What is the order of 2 in this group? What's the order of 2? So the answer is, how many times? The answer is, how many times am I going to multiply 2 to itself to get the identity 1? Just a minute. Now, so the question is, what's the order of 2 in Z3? That is this in this group. So the question is, how many times am I going to multiply 2 to get identity? Now, identity 1. How many times am I going to multiply 2 to get 1? So 2 ones will just be 2. 2 twice will be 1. 2 twice will be 1. So that means the order of 2, therefore, is 2. Because 2 times 2 gives me 1, mod 3. So that is about the order of an element in the single groups as we did last week. But today we want to look at what is the order of an element in a direct product group, which we also learned last week. We know what a direct product group is. So by definition, I've said the order of an element in a direct product group is the least common multiple of the orders of the component elements. The least common multiple. So just the same way I've looked at that example, I've been showing you this example. I've shown you the example of Z star 3, and I've shown you an example of, let me talk of Z3. Z3. So supposing I have a group Z3 cross Z star 3, and this is a direct product group. So I'm asking myself, what is the order of the element AB? What is the order of element AB, which is here? So for me to get the order of this element, by this definition, what I have to do, I have to get the order of A in this first group, get the order of B in this second group, and then the LCM of those orders gives me the order of this element. That is what this definition says, that the order of an element in a direct product group of a finite number of finite groups is the least common multiple of the orders of the component elements. So remember that the direct product group will be given several groups. I've just talked of 2 groups here, Z3 cross Z star 3, but it could be given so many groups, and a product of that could be given as Zn cross Zm cross Z P cross, and so on. And then you ask for the element. For instance, look at this. These are n groups, and I have n elements. So this element is coming from the first group, from the second group, and this, and so on up to the nth group. So the order of A1 in the first group, get order of AN in the last group required. So I just want us to look at a few examples to illustrate that, so that we get to the point clearly, how to get the order of an element of a group. This theorem just explains what I've been explaining, that the order of an element in this group, G cross H, will be the LCM of the orders of A and B. That is what. Now let's look at this. Let's look at this group. I began with a very simple element, 1, 1, element 1, 1, and it's in the group, direct product group for Z3 cross Z9. The question is, what's the order of 1, 1? So for me to find the order of 1, 1, I'll first of all find the order of 1 in this group, and then this other one comes from this other group. Again, I repeat what we mean by the order. The question is, These are additive groups. These are additive groups. They have no star. They have no star, so these are additive groups. So I'm asking myself, how many times am I going to add 3, get 0 in Z3? So the order of 1 in Z3 is how many times am I going to add 1? So you can see 1 once would just be 1, 1 twice would be 2, and then 1 3 times, 1 3 times would be 0. And so that means that the order of 1, therefore, is 3. So in the first group, the order of 1 is 3. And in the second group, the order of 1, it means I will add this 1 9 times to get 0. So the order of 1 in the first group is 3. The order of 1 in the second group is 9. And therefore, the order of 1 1, the order of 1 1, therefore, is the LCM. The LCM of this order is 3 and 9. The LCM of 3 and 9. And the LCM of 3 and 9 is 9. So that means the order of 1 1 is therefore 9. Now, this is the easiest way of doing it. And it's not the only way. We have other ways of doing this. And the thing is just understanding what the word order means. The word order, what it means, and that is what will help us. Now, let's look at another way of doing it. The one I've used here. I've said that we will also have obtained the same result by calculation. So from the word order, we understand what it means. We have two additive groups here, Z3 cross Z9. And the question is, what is the order of 1 1? So our answer is, how many times are you going to add 1 1 to itself to get 0 0, the identity? So that is how the other way we can look at it. The other way we can look at it without necessarily looking at the LCM. So I'm looking at these two ways so that as you write the program, you can choose one of the ways and use it. The first way that I've looked at, I said you would look for the order of 1 here, the LCM. The answer that you get as the orders, you would then get the LCM. The other way is from the definition of the order. From the definition of the order is, and these are additive groups. These are additive groups. So we are saying, what is the smallest element n, which we will add 1 1 n times. We want to add, how many times are we going to add 1 1 to get identity element? Now, so I began the first time when I add 1 1 once, I just get 1 1. Okay, so I was explaining the other way of writing this, getting this order, so that as you write the program, you can choose one of the ways to see which one to use. So the first one I said we would find the order of 1 from this and then 1 from this, and then get the LCM of that. But now from the definition of the order, again, we can try and see if we can write a program in that using the definition. And by definition, what we say is that how many times are we going to add 1 1 to itself to get the identity? How many times? How many times? And those number of times I've called them n. So we just begin doing it, and when we find 0 0, we stop, and then we read n at that point. once 1, 1, add it itself once, it will just be 1, 1. When I add 1, 1 twice, when I add 1, 1 twice, so 1 to itself, in fact, what I have is this, is 1, 1 plus 1, 1. And remember that these first elements are from the first group. So you add them and they give you 2. These other elements are from the second group. You add them, they give you 2. So 1, 1 twice, give me 2. 1, 1 thrice. So 1, 1 twice, 1, 1 thrice is like, is this. So if I just add here 1, 1, if I just add here 1, 1, these 2 had already given me 2, 2. Had already given me 2, 2. Then now I'm adding to that 1, 1. The first elements are from the first group. Give me 3, but mod is 3. So 2 plus 1 is 3, but the mod is 3. So 3 goes into itself once and the remainder is 0. And then these second elements are from the second group and the sum is 3. It's less than 9, so we just write it 3. So that's what we get. What about 4 times? So of course, it's very easy just multiplying inside. That's what of course, what I was doing. When you just multiply inside, this would be 4, but 4 mod 3. 4 mod 3, that would be 1. And this will also be 4, but we are doing it mod 9, so it remains 4. Then 5 times, we're adding 1 5 times. Again, this will be 5 mod 3, which is 2, and that will be 5. And then 6 times, this will be 6 mod 3, which is 0, and that will be 6 mod 9, which is just 6. And then 7 times, that will be 7 mod 3, and that gives you 1, because 3 will go into 7 twice, and the remainder will be 1. And then this will be 7. This will be 7 mod 9, which is 7. Then 8 times, this will be 8 mod 3, which is 2. And then that will be 8 mod 9. Then 9 times, this will be 9 mod 3, which is 0. And that will be 9 mod 9, which is again 0. So we've obtained the 0, 0 we were looking for, the identity element. And how many times have we added 1 to itself? 9 times. And therefore, that means the order of 1, 1 is 9. So that is when you use the definition of the order, when you understand what the order means. Because under addition, the order means the number of times we will add that element to itself to get the identity 0. Under multiplication, definition of order is the number of times we would multiply that element to itself to get the identity 1 under multiplication. I want to look at another example. This time, I want to look for 1, 1, 1. Now, when you're looking at 1, 1, that becomes very easy. Because the order of this one, of course, here will be 7. And the order of 1 here will be 10. And the LCM of 7 and 10 will be 70. So if you are doing it manually, using the LCM becomes easier. Becomes easier when you are using the LCM. But if you're not using the LCM, you can imagine you are to add this element itself 70 times. So it will take a very long time. So the LCM then becomes easier. And even if you are preparing a program, then again, the one that we're using LCM will be faster than this other one, because this other one will just be doing that, be doing what we've been doing, adding that element to itself 70 times. So it will be a bit longer. But this other one, just getting the order of that, because the order of that to be adding the element to itself 7 times, then adds the element to itself 10 times, then the LCM. So those number of times is not long. It will not take long to do that. Now, what about if we have a multiplicative group? Oh, there's this one also an additive group. I think I added this one just to make the point clear. What's the order of 5 there? So the order of 5 there, the number of times we are going to add 5 to itself to get 7, and not to get 0. To get 0. So 5 once is just 5. 5 twice is 10. Mod 7, that is 3. 5 thrice is like 8. Is 8. Because that would be 15 mod 7. But that's not what I did. I didn't do 15 mod 7 to get 8. I didn't do that. What I did was I discovered that 5 3 times is the same as 5 2 times. 5 2 times plus 5. But 5 2 times, I already have the answer as 3. Then plus 5, that is what I got, 8. I got 8, but you will have still have done this to get 15, then mod 7. Oh, it's mod 7. Eh? If it's mod 7, then this comes to 1 now. Comes to 1. Because it's mod 7. So I was saying it would have done it as 15, then divided by 7, the remainder is 1. Then what about 5 4 times? 5 4 times is the same as 5 3 times plus 5. 5 3 times plus 5. Or you will still have said 20 divided by 7, the remainder will be 6. Then what about 5 5 times? 5 5 times will be 5 4 times plus 5, which is 11 mod 7, that will be 4. Or if you want, you would just say this is 25. 25 divided by 7, the remainder would still be 4. And then 5 6 times. 5 6 times will be 2. Because this will be 4 plus 5, which is 9, mod 7, that is 2. 5 6 times, that will be 7, which is 0. 5 6 times. Now, so supposing anybody has a question, is good, as we said, you just ask the question, raise up your hand and then ask, because if you type in the chats, I may not see while the class is on. I may see it after we've moved some steps. And it's always good to answer the question while it's still fresh, while I'm still explaining the same concept, so that you understand it. Now, the order of the order of 5 in Z7, therefore, the order of 5, therefore, is 6. Now, we do the same thing now. This time, want to get the order of 6 in Z10. So we're asking ourselves, how many times, because Z10 is an additive group, you're asking yourselves, how many times are you going to add this 6 to get 0? Once will just be 6. Twice will be 2. 6 twice is 2. 6 thrice. 6 thrice. This will be 8. 6 4 times. This will be 4. And then 6 5 times. This will be 0. That will be 0. So the order of 6, therefore, is 5. Now we have the order of 5 and the order of 6, and therefore the order of the element 5, 6, as we have already said, is the LCM of these two, the LCM of these 6, and the LCM of these 5. And so the answer there is that what was the order of Z's, the order of 5? What was the order of 5? How come I gotten it as 7? Just go through again. Oh, the order of 5, this 5 times 6 gave us 30. Mod 2, mod 7, that was 2. So this was supposed to be 7. This was supposed to be 7. This was supposed to be 7 here. Because the order 6 times we had gotten 2. So what followed was 7 times what was to give us 7 as the order. So this would be the order of 7, the order of 5 therefore is 7. And the order of 6 is 5. And so the LCM of 7 and 5 is that 5 that I was getting. It's that 5. Now, so I didn't use the other way of the definition because it will mean that I add 5, 6 to itself, that 5 times, and that would be long. That would be long, but that is how the definition puts it. That is the definition of the order of an element. In an additive group, with the number of times you would add the element to itself to get the identity. So these elements, these 5, 6, to get the identity, you are to add it to itself that 5 times, and that will be long. So the use of the LCM now becomes shorter. The use of the LCM becomes shorter. Now, so example 85, I'll not look at it, because it's the same reasoning, but then you go through it and see whether you get the same result. We can even have 3 groups multiply together as we have the example 86. But then you're just getting the order of 2 in the first group, the order of 8 in the second group, and then the order of 6 in the third group. And then those orders get the LCM. So when I did the order of 2, for instance, I got that the order of 2 was 3. You can see 2 once was 2, 2 twice was 4, and the 2 3 times was 0. Because I'm doing it mod 6. 2 3 times is 6, which is 0. And therefore, the order of 2, therefore, is 3. Then I try to get the order of 8 mod 13, the order of 8 mod 13. And so 8 once give me 8. 8 twice is supposed to be 16, but because of mod 13, gives me 3. And then this is 24, mod 13, that gives me 11. So this is 3 times. 8 3 times is 11. So 8 4 times. 11 plus 8, which is 19. Mod 13, that gives me 6. So now I'm avoiding multiplying these bigger numbers because I don't have a calculator. But I know that 4 times, 8 4 times is the same as 8 3 times plus 8. And 8 3 times, I have the answer as 11. Then add 8 to it, gives me 19. Mod 13, that is 6. Now, what about 8 5 times? 8 5 times is 8 4 times plus 8. But 8 4 times is 6. Then plus 8, that will be 14. Mod 13, that gives me 1. What about 8 6 times? And so on. until you find that 8 13 times gives you the identity you're looking for. 8 13 times. That means the order of 8, therefore, is 13. And you see, this one, we didn't even want to, there was no reason of working out 8 mod 13. There was no reason of working out that one because of something we already talked about, that when these two, when 8, the element A and N are relatively prime, then the order of A will be the same as the order of the group. The order of A will be the same as the order of the group. So in this case, you can see that 8 and 13 are relatively prime. So since they are relatively prime, it's obvious, therefore, that the order of 8 will be the same as the order of the group, and the order of this group is 13, because they are relatively prime. But these 2 and 6 are not relatively prime, so that one you have to work out. And again, these 6 and 9, this 6 and this 9 are not relatively prime, so that one again, you have to work out. But where they are relatively prime, it becomes easier, especially when you're talking about additive groups. Additive groups are not multiplicative groups. Now, so in this example, therefore, the order of 2 we've seen is 3. The order of 8 we've seen is 13. And when you work out the order of 6, you find is 3. The order of 6 is 3. The working is here. It's 3. And therefore, the order of this element is the LCM of these orders, the LCM of these respective orders. And that LCM is 39. That LCM is 39. You know how we were getting the LCM in our primary school. This is how we were doing it. 3 will go here. Ones, 13, ones. Then 13 will go here. Ones, ones, ones. And therefore, the LCM is this product, which is 39. Now, so that is about additive groups. So then we have to come up with a code that will be giving us the order of elements in additive groups. But now I want to see, what about if somebody did multiply an additive group and a multiplicative group? And of course, we can also have multiplicative groups multiplied with the multiplicative groups. You can have Zn star multiplied by Zm star. And so again, you make a code for this. But let me show you where I've combined a multiplicative group and an additive group. Now, what is the identity of this element? Because the order of the element, what is the identity of the group? Now, the first group here is an additive group. So the identity of the additive group is 0. And the second group here is multiplicative, and its identity is 1. So the identity of this group, therefore, is 0, 1. Is 0, 1. So what is the order of this element? The order of this element is a number n, which, when you multiply by these elements, gives you the identity. Gives you the identity. So that number n is what you are looking for. So the question is, what is that n? So that n multiplied by 6. So when you add the 6 to itself, n times, when you add the 6 to itself, n times, you get 0. What is that n? And what is that n? So that 7 raised to n gives you 1. So that is what you're looking for. And that n therefore becomes the order. Now, if we use the issue of the LCM again, we'll still get the result correct. And if we use the definition, we'll still get the result correct. So long as you know what the identity element for this group is. The identity element for this group, since the first group is additive and the second group is multiplicative, the identity is 0, 1. So once you know the identity 0, 1 becomes easy. Now, so what is the order of 6 here? In other words, how many times are you going to add 6 to get 0? 6 once will be 6. 6 twice will be what? Be 12. Mod 8, that is 4. That is 4. 6 3 times. 6 3 times is 2. Mod 8. Mod 8. Because that is 12 plus that, which is 18. And if 8 were to go into 18, the remainder would be 2. Alternatively, these two, the answer is 4. So this 4 plus this 6 is 10. Mod 8 gives you 2. Gives you 2. What about 6 3 times? No, 6 6 3 6. This was 6 3 times. So we are doing 6 4 times. 6 4 times. Now 6 3 times is 2. So 6 4 times would be 0. Would be 0. And therefore the order of 6 therefore is 1 2 3 4 times is 4. The order of 6 therefore is 4. What about the order of 7 in this multiplicative group? Want to do it until we get the identity 1. 7 once is just 7. This time I'm multiplying. We're not adding because we're not dealing with a multiplicative group. So we're adding, multiplying 7. So 7 twice. 7 twice is 49. How many times does 18 go into 49? And what is the remainder? So that is the question. How many times? So let me just, of course, there's 36 somewhere. So 49 divided by, it's 18. You go there twice. So the remainder is 13. You could also use your calculator so that we move together so that, so because if I mess, then we'll have to repeat and it will take a long time. 7 3 times, or yes, 7 3 times will be 13 times 7. 13 times 7, because 7 twice is already 13. So 13 times 7, which is 96. 96 divided by 18, because there are 5 times. What's the remainder? The remainder is 1. So that therefore means that the order of 7 is 3. The order of 7 is therefore 3. What about the order of 6 7? What about the order of 6 7? This will be the LCM of 4 and 3, which is 12. So that's how we do that. And of course, you would have used the definition. But if you do that, you will have to do that 12 times. How would you do that? Just show you how you do that. Then from there, we go to the codes and see how the codes, how I wrote them. And of course, you can modify the codes using any style Now, the method I want to use now is the definition, the one of the definition, but you can see that we're going to do that 12 times, so it will not be easy. So let's try it. So let's just do it. It is 6, 7 once. When you do it once, we know that for the first element, we are adding the first element, the number of times we are putting outside. And the second element, we are raising it that element. So in this case, 6 ones will just be 6, and 7 raised to 1 will be 7. Okay, what about when our n is 2? When our n is 2, so that means 6 twice, and we are doing it mod 8. Mod 8, that will be 4. Mod 8, because that will be 12. 12 mod 8, that will be 4. And then the second element, we raise it to 2, that will be 49. And it's mod 18. 49. Let's again do it using my calculator. 49, we are done. We had found 13, I think. So that will be 49 divided by 18, go that twice, and the remainder is 13. Okay, we are done with the 2 times. Let's now do it 3 times. 6, I just want to show you a few times, then you can continue with that. 6 3 times, and we are doing it mod 8. And remember, when we did 2 times, it was 4. And then the third time, so you're adding 6 the third time, to be 10, which is 2. And then 7 raised to 3. 7 raised to 3. 7 raised to 2 was giving us 13. 7 raised to 3. 7 raised to 3 just same as 7 raised to 2 times 7. But 7 raised to 2 is 13. Then times 7, that gives us 91. That gives us 91. That 91 divided by 18 is 5 times. 5 times, and the remainder is 1. So you don't stop here because you've found this identity. You continue until the number here is 0. The number here must be 0, and the number here must be 1. So then you come 4 times. 4 times. But the good thing, this one will just remain, it will help us a lot. Can help us a lot there. But now, what is this 6 4 times? 6 3 times was 4, was 2. When you add another 6, that will be 0. When you add another 6, that will be 0. Or you just multiply this. That will be 24 divided by 8. The remainder is 0. And then what about 7 4 times? 7 4 times. 7 3 times was giving us 1. So when we talk of 7 4 times, is 7 3 times 7, but this is 1. So that gives us 7. What about 5 times? So this will be 30. 30 divided by 8. What will be the remainder? The remainder, of course, is supposed to be 6. I've just taken this 0 plus this. 4 times. 4 times was giving us that. So 5 times will be this times 6, which is 6. And then 7 times 7 will be 49. And that had given us at 1.13. And so on. So when you continue that, at the time you arrive at 12 times, you would get 0, 1. By the time you arrive at 12 times, you get the identity. Okay, that's what you'll do. You can try that later and see whether you get what I've said. And if you don't get it, we can still look at it together and see whether we see that we get it. Now, this one I will not do it because you now know what to do. These are both multiplicative groups, so we know the identity element will be 1, 1. The identity element will be 1, 1. So you're asking yourself, how many times are you going to multiply 16 mod 23 to get 1? And then you're asking yourself, how many times are you going to add multiply 43 to itself mod 52 to get 1? Okay. So I think at this time I should now go to the code and then we look at how the code works so that I can also explain how it works, how to write it, and then how it works. I began by saying, recall that the order of this element is the least common multiple. So that is the method I'm going to use. Is the least common multiple of the orders of A and B. In other words, that small element K, which when multiplied by A and B, gives us 0, 0. So that's the method I use, the least common multiple. And the reason was I discovered it would be shorter than the other one. Of course, the other one will still give us the same result, but it will be longer because of the steps involved. And of course, when you're dealing with a huge number, then the steps become even longer. So here is the code. I have the part for determining the GCD. Then I have the part for determining the LCM. And of course, the LCM is the same as the product of A times B over the GCD of A and B. And then they have this part for getting the order of the elements. We had already looked at this example later, where the order of an element, is the order of the group over the GCD of the element and the group. This is for an additive group, not a multiplicative group. We had looked at this earlier in our early examples. Not today, but earlier examples. I can just show you again. And just show you using this example, the order of 2, this is an additive group. So again, this is a shorter way than the one I'm using here. The order of this 2 in this group is the order of the group, which is 6. The order of the group, which is 6, over the GCD of 2 and 6. So this will be 6, and the GCD of 26 is just 2. That gives us 3. The 3 we got here. That's the 3 we got here. We looked at this method earlier. Now, again, what will be the order of 8 in Z13? Will be the order of this group. The order of this group is 13. Over the GCD of 8 and 13, these two elements are relatively prime. The GCD is 1, and so the order is 13. What about the order of 6? Here, the order of 6, the group has 9 elements, and then the GCD of 6 and 9 is 3. So this is 9 out of 3, which is 3. So that's how you get those orders in an easier way. And that is the way I used. That is the easier way that I used in my code. Because again, it gives me fewer steps. Gives me fewer steps than the one of adding the element to itself several number of times. So that when you are dealing with a very big number, then you have so many number of times you have to add it to itself. Now, so that is what I used in my code. So this part, therefore, the one I'm erasing, the part, the additive order function, will be getting the order of the element in the group, the order of the element in the group. And so it will be using the formula we just talked about, where the formula is n, that is the order of the group over the GCD of the element and the group, the order. So that is what this part will be doing. What about this other part? This other part will be doing what we already said, that after it has gotten the order of A and gotten the order of B, now the order of A and B, this element, will be the LCM of their orders. The LCM of their orders. And earlier on, we had said the LCM, the easiest way of writing the LCM using a code is by getting the product of the two elements over the GCD of the two elements. This we said earlier when you were writing the code for getting the LCM. We said for you to compute the LCM of two elements. For instance, if I have 2 and 3, the LCM of these two elements is their product. Let me talk of another element. Let me talk of 3 and 9, or 3 and 12. Talk of 3 and 12. What is the LCM? So the LCM of these two elements is their product over their GCD. The GCD of these two elements is 3. Which element was I talking about? I was talking about, it was 12 or 13. So what is the LCM? So the LCM is this, which is 12. So the product of the two elements over the GCD of the two elements. Their product is 36 and their GCD is 3. So this part is therefore getting the order of the element AB. The order of the element AB. So after getting it has to get the order of A and then get the order of B. And so this GCD, you know what it will be doing? This GCD is what we are using here. This GCD is what we are using here. That is why we have that part of the GCD, because it's then used to get the LCM. You cannot get the GCD before getting the LCM. You must have the LCM. No, you cannot get the LCM before getting GCD. You must have GCD first, then the product of the two elements, then you divide. I want to show you the code, how it works. I begin with the additive groups. Two additive groups. This is the code. This is where I have my F, the main function. My A and my B. My groups, mod N, where N is 8, and mod M, where M is 12. So the first element, 6, is coming from this first group, mod 8. And then the second element, 9, is coming from this group, mod 12. So what do I expect as my result? My result would be the order of first element 6, second element 9, then Z mod 9 cross Z mod 12 is, so that's what I'm expecting. Let me just run this code and see, then it tells us. So yes, so after running it, you can see at the bottom, the result is there and it's saying the order of 6 and 9, that element in Z8 cross Z12 is 4. Is 4. So we can change the elements, make them slightly bigger. So let me also make the group bigger. And then make this other element also bigger. And make the group in which it is also bigger. And see whether it will give us. So although I've not used big units, but let's see whether it will give us. You can also use big units when you're dealing with the big numbers. Okay, it has given us the order of 247 and 99 in Z886 and Z cross Z612 as this. That means that element, you can add it 30,124 times to get the identity 00. You can add it those number of times. Then I can also show you the multiplicative one so that I explain both. Now, I've also created another one for where the groups are combined, mixed, additive, but this one is just for multiplicative group, cross multiplicative group. You can see where I have highlighted. It is Zn star cross Zm star. So that means this element 991, but this group, I think I've used a bigger unit. I've used, oh, yes. So this will assist us to handle even bigger numbers. Now, so I have 1081, the first group mod 1081, the second group mod 1481. And this is second element B in the second group. So then, therefore, it will print to us. This is what it will print. It will print the order of 991 and 1396 in the Z that and Z that is that. So let's just run and see what it gives us. It has given us a result at the bottom. You can see the order. Now, I'd already explained how this code will work, but then I have formal notes for the explanation. Of course, you know how the GCD is calculated using this code. The GCD, what does it say here? Supposing you entered end B, where B is 0, then the code will say that if B is 0, then the GCD is A. So that is what it is. So for instance, if I have 8 and 0, the GCD of this is A, which is 8. So that's what the code is saying here. That if B is equal to 0, then A is the result. Otherwise, if B is not 0, then what is the GCD? Now, it will divide A by B until B becomes 0. So what happens is, supposing I have 8 and 3, and I want to get the GCD, the first thing it does, it will calculate the GCD of 3. I wanted the GCD of 8 and 3. So the first call is the GCD of 3 and the remainder of A on division by 3. So this is same as the GCD of 3 and 2. The GCD of 3 and 2. So B now is 2. Remember it was 3, is now 2. Because 3 divided into 8, the remainder is 2. Now the other call is now the GCD. We do this until B is 0. If B is 0, the GCD becomes A. If B is 0, the GCD becomes A. So that's what we are doing here. This is what we are doing. So it will now call for the GCD of 2 and 3 on division by A. And on division by B. So what was B comes here, then A is divided by B, the B which was there. So A is 3 divided by 2, this 2. So of course, this is a GCD of 2. Let me write here, of 2. The remainder there is 1. The remainder there is 1. So the next call, therefore, the GCD of 1 and then 2 on division by 1, what is the remainder? So that is a GCD of 1 and 0. So because 2 divided by 1, the remainder is 0. So the GCD becomes A because B is now 0. B is now 0. So the GCD is A from this base. So the GCD of the numbers that we began with this. These are the numbers we began with. So the GCD of 8 and 3, therefore, is 1. So that is how the code is going to do to get the GCD at that point. Those are the steps the code will use. The code will use that. So it's doing that until B becomes 0. So when B becomes 0, then A becomes the GCD. A becomes the GCD. So that is what is happening at this point. At the point of the GCD. And I've already explained what is happening at the point of the LCM. Once the GCD has been obtained, now that GCD is now assisting us to get the orders of the elements in their respective groups. In their respective groups. So you know what is happening is this. What is happening is you want the order of two. Let me talk of 8. We talk of 8, 3, because I've already done that. You want the order of this in the group Z10 cross Z5, for instance. So it has to get the order of Z, no, the order of 8 there. It has to get the order of 8 there. So what is the order of 8 here? Of course, it will be doing it this way. Be doing it that way. So it will be using this part to get the order of 8. So it will then do, the order of 8 will be 10 out of the GCD of 10 and 8. But where is that GCD? The GCD is done here. The GCD of 10 and 8 is done here. So after getting the GCD of 10 and 8, that GCD of 10 and 8 comes and is, so you can see this. So this is calling from this part, it's calling the GCD of this part. It's calling on this function. So it's asking for the n divided by the GCD of n, a and n. So this function does that. So after doing that, this one picks it and then gets the order of 8. The order of 8. So let me say, for instance, here the GCD is 2. So the order of 8 here will be 5. So this one gets the GCD as 2. And then this one takes that GCD, puts it here, the order will be 5. Now what about the order of 3 here? The order of 3, again, it comes here, comes at this point, supposed to be 5 over the GCD of 5 and 3. So this one calculates the GCD and gets 1. And so 5 over 1, 5 over 1, that again is 5. So the order of 3 again is 5. So once this one has gotten the order of 8 and the order of 3, this one performs the order of the element we wanted, 8, 3. It performs that. How does it do that? It knows that the order will be the LCM of the two elements, the LCM of 5 and 5, the two orders, the LCM of 5 and 5. So for it to do this, it takes 5 times 5, then divided by the GCD of 5 and 5. So again, this one has another function to do, to get the GCD of 5 and 5, which of course is 5. So that on doing that arithmetic gives us 5 as the order of the element. So that is what is happening. And then we also have the main function and its functions and what it is also doing. Now, some of these parts you can do away with them and combine one part with several functions. You can do away with this, some of these functions and combine. I also have this other one. What this one is saying says let add order A. Let add order A. So that is, for instance, if you're getting the order of A, so I've said here is a function to compute the order of this element. in this. So initially, it takes the order of A to be this. So that is the initial part. So the order of A from that part. So it takes it initially to be AN. Then the order of B initially is taken to be BM. Then the LCM of the two gives you the order of, and of course, that is what you already explained. So the LCM of the two. So initially, it finds the order. Of course, these results are coming from above. So the order of A in N, in mod N, and then the order of B mod M, then the LCM of those two. The LCM of those two gives you the order. Now, so you can go through, I've already explained what each of these parts is doing. So you can go through it later and understand what is happening. Of course, this formula I've already explained what it does. And each of these parts I've already explained. So the order of A in Zn is calculated as the order of Zn over the GCD. Then this is the last part I was explaining. That the order of this element will just be the least common multiple of the LCM of A and B. The orders of A and B, the orders of A and B. So the LCM of the orders of A and B will be the order of this element. So this part does not have a lot of things to do. It's just taking the LCM and then the main function writes that. So the main function then, after initializing the elements you're inputting, the other role is just to call on the order function and then reads the order. Now, the one for where there's a multiplicative groups is a bit long, slightly longer, because one, it has this part, and this part is just to get the order of the element in N. Supposing you have element A in Zn star. So it's getting the order of the element here. And then we have this other part, this other function that will now be doing the order of this pair, AB. After this one has already done, after this one, see this one will have to get the order of A and then get the order of B. Then this one now combines the two and gets the order. Then I have this other part. Oh, this one was the longer one was the other one. So this one is a bit shorter. But now the calculations are a bit somehow longer. For instance, how do you get the order of A in Zn? So the first thing, you let the order be 1 and is mutable. Let the order be 1. So for instance, I want to get the order of 3 in Z star 5. So the first thing I will do, I will say let the order be 1. Let the order be 1. And that one will be changing. Then I also have the power. Let the power be A on division by N, the remainder. So 3 divided by 5. The remainder of that is 3. The remainder of that is 3. That's all you write. Then there's a loop. There's a while loop. And the while loop says, if the power is not equal to 1, if the power is not equal to 1, then you calculate the new power. You calculate the new power. So for instance, in this case, the power is not equal to 1. So since it's not equal to 1, we get the new power. And the new power will be the power we already have, which is 3, multiplied by A. Our A was here. Our A is 3. The result that you get divided by N. Divided by N, our N is 5. Then you write the remainder. Then you write the remainder. The remainder is 4. And then our order was initially 1. So when this happens, you increase the order by 1. So that we now go to order is now 2. Order is now 2. Now this process continues until the power is 1. This process continues until the power is 1. So you can see my power is 4. So since my power is 4, we get the new power. We get the new power. And how do we get it? Get it by taking the old power and then multiply by A. Our A is 3. And then the result divided by 5. This will be 12 divided by 5. Answer is 2. And then the order increases by 1. The order increases by 1. So I'm just reading here. Just reading the formula here. Now, the power is not 1. The power is not 1. So again, we go another way. Now a new power again is the old power, which is 2 times A. Our A is 3, and then divide by 5. The remainder is 1. This happens until this condition is here. Condition is here. The condition says, while the power is not equal to 1. So this continues until the power is 1. So the power is 1. We just say the order, therefore. The order, therefore, is 4 because we've done this calculation. The order is 4. And so that it becomes the answer. So we exit the loop. Since our power is now 1, we exit the loop. That is how this part is going to work. So the good thing is that this is a video, so when they share the link, you can listen to that calculation, how I've done the calculation up to the point of declaring the order. So that means our 3 here, when you raise it to 4 times, should give us 1, because 3 twice would be 9. 9 times 9, of course, gives us 1. So the order is 4. So you increment the order by 1. That is what this part says. That's what this part says. And then it says, while the power is not equal to 1. So once the power becomes 1, you exit the loop. And when you exit the loop, you read the order. The order is there for 4. So that is how it will be working. And of course, again, you look what I've included the workings here. Of course, without those explanations, but of course, when you listen to the link, you can hear the explanations. But how the code works is included here. So then you attempt these questions. So we've already covered these questions. You attempt the exercise questions are here. You attempt them. If you find any problem, we can always look at them together. In this question 9, you can use your Rust code. So you come up with a Rust code, then do this question 9. Thank you.